Hi, I'm Yanzo. Today I'll talk about stealing input data from TEE-shielded neural networks with Ciphertext side channels. Modern deep neural networks are fascinating black boxes that allow you to feed them input data and get answers. Sometimes your input data is not a secret, sure, but other times it may get much more personal. For example, what if it's your facial photo, your biometric data, or the genetic information that literally makes up you? So input data are important, and besides the profound risk of user privacy compromise, leaked user inputs can also lead to model and intellectual property stealing. To protect against this, people put the model into trusted execution environments, or TEEs. TEEs are hardware-backed, so even a privileged malicious host can't see what's inside the environment. From a 10,000-foot view, TEEs work by encrypting memory regions. Because it's directly done by the hardware, the malicious host will only be able to read the encrypted ciphertext, but never the plain text. Well, that sounds great, so we're safe now, right? Well, the good news is that modern encryption algorithms are generally considered secure, and it's basically impossible for attackers to decrypt protected memory content. However, that doesn't prevent side-channel attacks. You see, TEEs need to support the encryption of large memory regions, and they also need to support random access to encrypted regions while keeping it efficient. Therefore, most TEEs use deterministic encryption, which means that every time we try to write the same data to the same memory address, the resulting ciphertext is the same, and we call that a ciphertext collision. This is where the side channel lies. For example, when you're processing a bit stream, which can be the case for cryptographic keys, the attacker may be able to observe the changes in the encrypted memory and determine the value of each bit, and eventually steal the key. But while that works well for bit vectors, it's not the case for neural networks. The data in DNNs are usually floating point numbers, which have much wider ranges for values, so collisions almost never happen. So is that the end of the story? Fortunately, nonlinearity comes to our rescue. Nonlinear activation functions are core to modern AI's intelligence because they empower DNNs to break free of linear limitations. Importantly, these functions typically map values from a larger range to a much smaller one, and thus significantly increase the chance of ciphertext collisions. Great, now how do we do this? The most straightforward idea is, of course, just to train a neural network to recover the data from the side channel trace, but that didn't quite work. The recovered data is pretty far away from the ground truth, as you can see here. And we soon realized what the problem was. There was too much information lost in the side channel trace, and not really enough information to fully recover the data. So we need some help to reconstruct the data. One insight is that real-world data is not just random. They follow constraints. For example, while the first image looks real or semantically meaningful, the rest don't. So if we have some knowledge about what real-world data looks like, that may help us reconstruct the lost information. Now, suppose we have that prior knowledge. How can we make use of that? We can kind of flip the procedure around using Bayes' theorem. So before, we are trying to produce an image given our observation. But what if we try to find an image that produces our observation instead? Specifically, we do this in two steps. First, we generate an image, and at this step, we can use our understanding on real-world images to guide us. Then, we deconstruct the generated image using rules we learned by profiling the victim model. In other words, we are simulating the information loss happening with side-channel observations. Finally, we can minimize the distance between our deconstructed image with the coarse-grained image we had before. And we can use this minimization objective to guide our generation, or our guess. So maybe we'll start with this guess here, optimize our guess, further optimize our guess until we reach an optimum. So now, because the deconstructed image matches the coarse-grained image we had, our generated input should also match the secret image we want to steal. And this worked pretty well. We had high success rates for both our objectives, user privacy compromise and model stealing. Here are some examples of the recovered data, and you'll see that they're pretty close to the ground truth. And it works for videos too. If you want to see more of these examples, just simply go to our website. Finally, we also did some experiments on different neural network runtimes, including interpreter-based ones like PyTorch and also compiler-based ones like TVM. And we found that various primitive operators and almost all compiled layers cause a side channel. In other words, the leakage is pervasive. So today, we talked about how TEEs don't protect your DNN inputs, where DNN's nonlinearity contributed greatly. We transformed the recovery problem to a generate and deconstruct problem, and the results are satisfying. Thank you.